unfortunately, with this part, I've got my notes spread out over several different notebooks.
Well, radio frequencies, they, according to the federal regulations, they have to keep your frequency in a certain bandwidth because you're dealing with harmonics. Because if you don't, you can always listen to somebody else's frequencies, which is in that range of harmonics.
Yeah, how? Just a second. And there are times, especially at night, we used to be able to, when we lived in Richmond, we used to be able to pick up a Cleveland radio station at night on certain nights.
Richmond, Virginia?
Yes.
Well, that calls from the atmosphere, because we used to call that skip, because the highway patrol used to be on low band radio, and their low band radios is the same frequencies as our low band radio, but they separated by Earth, and due to the weather, we call that skip, because you could hear them on Highway 101 down in California, and we on Highway 5, and we over here on 85.
Oh.
And we used to call that skip.
Yeah, our radio wasn't as powerful as the one you were working with. That's why we couldn't get California.
Because of the Earth, the weather and the Earth dynamics to it.
Yeah, I was going somewhere with that. I lost it. All right. Now, regardless of the waves, if we're talking about a transverse wave, I would draw the transverse wave pretty much as you would see it. So if I was drawing what I had out there, I could draw a transverse wave looking like that, maybe an arrow pointing which way the wave is moving. So transverse waves, typically what you see is just a snapshot of it. The exception to that is if I have a standing wave out there, typically there'll be nodes, so you've got these points which are not moving. And the antinodes are generally represented, so I got a wave like that, but you typically represent a standing wave like this, where you have the antinodes here. Antinodes. And then you have the nodes here. And I'm not saying this is in two places at once, I'm saying that it's vibrating back and forth here. Longitudinal waves, on the other hand, what you're actually seeing is not a snapshot of what you're visually seeing in terms of the wave. So for example, for air, or take the sound for example, you'll have a bunch of air molecules really next to each other, close to each other, and then you'll have fewer, and then you'll have a bunch next to each other, and then there'll be fewer, and then a bunch next to each other. Caused by, you got a vocal cord here. When it goes that way, it pushes air together here, so you get the high, assuming this is the way out. You get the high pressure here. When the vocal cord snaps back, you basically, small little vacuum. But you get these areas with less air, because it's pushing the air behind it. And so by your vocal cord vibrating back and forth, you get these areas of compression and rarefaction. Now, to represent this in terms of a graph, drawing the dots to actually show sort of molecule placement is not particularly convenient, so there's got to be a simpler way of doing it. So the two ways that I would represent this in terms of lines, give myself a little bit more room. So I got much right here, less here, much. So this is the part that's gonna push your eardrum in, this is the part that's gonna basically suck your eardrum out. But I could represent this in terms of a pressure, got high pressure, low pressure, high pressure, low pressure, high pressure. So if this is a longitudinal wave, this would represent potentially, this is compression, rarefaction in the case of sound. In the case of slinky, it's the coils really close to each other versus the coils farther apart. So I can put down high pressure slash density. And then low. So when I'm drawing waves and I draw it like this, usually it would represent either longitudinal or transverse, just the interpretation of it's a little bit different. And the other way I can represent this is, I can just draw a line where the high pressure is. And so these lines represent high pressure. And then low pressure would be in the middle. This is like the ripples in the pond. You throw a stone into a pond, you get these ripples going out. Where the peak is the highest, basically the ripple that you're seeing, would be an analog to the high pressure. And if I threw several stones in the exact same spot, and I get several ripples, and have high pressure basically created by the, well, that is the ripple, and then in between would be the low pressure. When dealing with high pressure, low pressure, or dealing with the slinky, or if I just have the slinky like this, there's a certain automatic distance between the coils. Now, the coils, it's not the same all the way down because of gravitational pull, but the essence is there. There's a certain distance between them, sort of the ambient distance. Or with air, there's a certain pressure automatically in the air, whether there's any sound being made. So there's this middle section right here, which is sort of the ambient. Sure, I'll assume it's still right. The ambient pressure. Or density. And so when we're talking about high pressure, low pressure, it's not relative to some arbitrary scale, it's in reference to what the environment is at that moment. And so this distance from here to here, or here to here.
Isn't it spelled with an E? Ambient?
I was thinking it had an E in there, but it didn't quite,
Yeah, that's.
Ambient.
neither of them look right to me right now. And this is the amplitude. So we get into some of the vocabulary words.
Yeah, it's E.
Okay, thank you. When I wrote it down, my mind said E, but then I thought, no, that's not the way I pronounce it. It seems like it should be an A. Perhaps I should pronounce it differently. So amplitude is basically, I'm gonna put distance in quotation marks because it's not necessarily a physical distance, but distance from
The ambient to.
the median or the middle to peak or to trough valley, however you want to word it. Max and min.
There's two words, there's ambiance and ambient.
Ah,
There's not an ambient.
all right, so if it's CE, then it's an A.
Yeah,
Okay, all right.
it's very confusing.
English.
Yeah.
All right, you've seen the English we don't borrow from other languages. We follow them dark alleys. mug them and take loose grammar from their pockets and spelling. Okay, period. If I have several different waves being created, we've talked about period before, about if I have repetitive motion, is how long it takes to do one type of that, and the same is true here. So the time to create one full wave. Wavelength. How far a wave travels in one period. Frequency. Which we've talked about before also, is
1 over time.
1 over the period, or that's how often a wave is produced. Probably better wording instead of how often. I mean, in essence, it means the same thing. I'll put them both down. How often a wave is produced. Also, 1 over the period. Also, the number of waves produced in a set time. So if I produce 5 waves every second, my frequency is 5 waves a second. How often is it produced? Well, I produce a wave 5 times a second. Let's talk about units.
Hertz,
For which one?
frequency.
So the SI unit of frequency is hertz. The symbol for period, which we've done before, is a capital T. What's the SI unit for period?
Second.
Second.
Symbol for wavelength is a lambda. What's the SI unit for wavelength?
Nanometers?
Pardon?
Nanometers? Oh,
Uh,
meters?
Meters.
I'm thinking of light, I'm like,
Yeah. Then there are the standards that are used because of tradition. It's like density. Density in SI units would be kilograms per cubic meter, but there are a lot of tables out there which still do grams per cubic centimeter, even though it's not officially international standard. And if you weren't quite thinking of light the way that John was going about it, that meters, it's a wavelength. It is a length. And then the SI units of amplitude.
meters.
Or Nick got us that far. Someone else want to give another one?
Centimeters.
Not officially SI.
Wouldn't it be in hertz too? Because it'd be
I
a
don't know
cycle.
if I've seen a situation where it would be in hertz.
No, seconds per.
Would it be meters a second?
Could be meters per second. I guess it could, it depends upon if you're oscillating the frequency. I guess frequency modulation. That'd be one in there too. What I'm getting towards is that the amplitude units depend upon the situation. If I'm talking about sound, if I'm using the lab quest to measure sound, it's gonna give, I can get an amplitude in pascals. If I'm talking about what we were doing out there in the hallway, well, then meters would be the SI unit, because that was a physical distance. So it really depends upon what type of wave it is and what's actually being measured. The symbol for amplitude is usually case specific. I often just use the letter A. Frequency, have I talked about the letter nu for frequency?
I don't think so.
All right. As is indicated right here, and as we did before, I'm using the letter F for frequency. If you look at some textbooks or some other sources, not every source will use F for frequency. The most common one that you will see in more advanced books is the nu.
Oh, you use that for response ratio.
Yeah. I mean, again, we have 100 letters of, 100 letters, uppercase, lowercase, Greek letters, our letters. We run out, we have to repeat. But nu is often used. Now, the biggest trouble with using the letter nu is it looks too much like a V.
Yep.
So let's talk about a speed of a wave. So first off, what is the formula for speed?
Changing displacement over time.
Time.
Okay,
Wouldn't speed be distance over time?
it would be. And I was gonna nitpick, but thank you. Appreciate you doing it. So speed is distance over time. So if we're talking about one wave being produced, so I'm out there and I give a pulse to it, the time it takes to produce that one wave is the period. And what is the distance that a wave travels in that period?
1/2.
That would be the frequency. I'm looking for the distance.
Oh, the distance.
What is the distance traveled in one period?
The wavelength.
Yes. So the speed of the wave is also, for a traveling wave, we have the wavelength divided by the period. The period is just 1/2 the frequency, so that's 1/2 the period times the wavelength, which is just frequency times the wavelength. So this is a common equation. I've seen this in elementary to advanced textbooks, but slightly different form. Now, if I use the letter nu for the frequency, this equation would look like this. Except for the fact that some textbooks use a slightly different font, and in some fonts, it will look like this.
You have 3/4 of an X and a V that's slightly blown over.
Yeah, but the question is that the V, or is that the V, or is that the V? Which one of those is the V, which one of them is the nu?
You just gotta know.
What I do is I look for this equation to figure out what font that they're using so that I know which one is their V and which one is their nu. It is a real pain in the butt. So that is why I use the letter F instead of the letter nu. Also, F for frequency, it makes sense for English-speaking audiences. However, just please be aware, if you're looking at other sources, you might run into this. My first year here, I sat in my office and one of the nanotech students came in and said, I have a question for you, do you have time? And I said, sure. She said, why are there 2 V's in this equation? I said, oh, yeah, no, one of those is not a V. So it's not readily obvious when you look at the equation of going, oh, okay, it's, at least, I'm hoping at this point, it sunk in for the student.
I appreciate you not using a V for frequency.
Or nu.
Or new, yeah.
They use that in the textbook.
Yeah, your textbook does not. Thank goodness. Now, there are two directions to go in. So let's talk about a wave that's actually being produced here. So I have a wave that's traveling this way. I want to concentrate on just this piece right here. If you think about it, if I'm producing a wave, so let's say I'm starting here, I'm moving out, I'm back, and then back to where I started. So basically my hand motion with the first time would look something like that. Starting here, moving out, coming back, and then back to where I started. What function is that?
Sine.
Yeah. So my hand motion is basically a sine wave. Now it doesn't necessarily have to be, but it's probably a pretty darn good approximation because I start at 0 in terms of speed of my hand. I move out to some maximum, I move out to some point where my speed is 0 again. I move back, I'm at 0 again, and then I come back to where I started. This actually would model my position as a sine wave. But we just talked about the fact that these trig functions also define simple harmonic motion. So I have this point right here, which is basically, if I'm doing a full wave back and forth, this piece right here is sort of undergoing simple harmonic motion. It starts here, it moves up, stops, moves back, stops. If I can produce several waves, it just oscillate back and forth. So let's take a look at the forces that are acting at that spot. So sort of do a blow up of it. I'm interested in the point right there at the very top. What's the direction of the forces acting at that point on the road?